In this bonus chapter, we will take a first look into the world of machine learning. We will use our own generated dataset to train a model that then allows us to make predictions on new data. More specifically, in this chapter, we will explore linear regression and logistic regression and how to implement these algorithms using Python code. So let's dive into the slides and see how this is done. Now, to learn about regression, we expand on our knowledge that we acquired in the previous chapter about correlation. There, we learned that two datasets can be correlated to each other, indicating a connection between the values of these two datasets. Now, this results in a coefficient that quantifies the extent of this correlation or this interaction between these two datasets. And it is therefore that the correlation coefficient is a fundamentally descriptive measure of our data. But in this case, we want to take it a step further. We want to use our existing dataset to train a model that allows us to make predictions on new data that is given to us. And to illustrate how this works, let's look at an extreme example. Let's say that we have two datasets, X and Y, and we have determined that these two datasets are in fact perfectly linearly correlated. This means that we can determine with 100% accuracy any value in our Y dataset from the corresponding value in the X dataset. Now, this is of course encoded in this formula right here, which shows the perfect linear connection between X and Y. Because for each value in Y, we simply multiply the corresponding value in X with a fixed number A, and then we add to this another fixed number B. Now, because we have this perfect formula, what we can do is we can use it to predict new values. Let's say that we are given a new value of X that wasn't present in our original dataset X. Now, to get the corresponding prediction for this X, namely the predicted Y value, we simply multiply it with this fixed number A, and then we add this other fixed number B. And this gives us the exact value of Y. Now, of course, in real life, two datasets X and Y are never perfectly correlated. And therefore, the information from this fixed number A and fixed number B, the values of these numbers, are of course unknown to us. And this brings us to the challenge of regression. Namely, by just looking at our dataset, so values in X and values in Y, and trying to abstract the best values for A and B that fits our dataset best. And then when we have obtained this A and B, we can use them in this formula to make predictions about new values of Y. Now, as was the case in correlation, we can have different types of variables. We can have two continuous variables or two categorical variables, or even in the case of regression, a combination of the two. Now, as you might expect, these different cases require different algorithms to solve. And we will start with the case of continuous variables. And this will bring us to linear regression. To start off, as we always do, we want to generate our own datasets in such a way that we can simulate a variety of different scenarios. Now, in this case, we again need two datasets, X and Y. And the conditions on these two datasets are very similar to the previous chapter. Of course, X and Y must be correlated, but also we need to make sure that we can fine-tune this correlation. The next requirement is that the correlation between X and Y needs to be linear, meaning that if we scatter our data points, they must roughly lie on a straight line. And the final requirement is that both X and Y need to be approximately normally distributed. So let's now look at the strategy to generate these two datasets. The first step is to generate X according to a normal distribution. This normal distribution will be centered around 0 and have a standard deviation of 0.4. And then to make this linearly correlated to another dataset Y, we generate our new dataset Y by using this linear formula. So we multiply X or any value in X with a number A, and we add to this another number B. What we did in the previous chapter is we took this A to be a fixed number throughout the two datasets. However, for this B, we generated a random number, a different number for each pair of two variables. However, because in this chapter, we are going to simulate how to discover this A and B from two datasets or underlying data, what we're going to do here is for both a and b, we're going to generate random numbers. This means that each y is generated from x with a slightly different number a and a slightly different number b. And this gives us the condition that a and b for each pair of two variables are noisy random variables. So let's now briefly hop over to the Jupyter notebook and see how we can implement this strategy and generate these two datasets using Python code. The first thing that we're going to do here is we're going to define some variables, and these variables will be used to generate our two datasets. First, we define this number a and b, and at this point they're still fixed values, but we're going to use these to generate random numbers that deviate slightly from these variables. And then looking ahead already, what we're going to do with our algorithm, our linear regression algorithm, is trying to recover these two values by just looking at our random data. And then next we define a noise parameter, which indicates the standard deviation of these two random variables a and b, and we're going to define a size, which will be the number of data points in both x and y. Then we're going to define x and y. As said before, the values in our x dataset will be randomly distributed according to a normal distribution. The mean will be 0 and the standard deviation will be 0.4. And then from this x, we define our y dataset, which will be linearly correlated with it. And here, what we see is the formula that we had before. So this will be the number with which we want to multiply the values in x. Now, in this case, it's not just a single number, but each time we're going to generate a random number according to a normal distribution, which is centered around this value a, which is 1 in this case. Then the standard deviation of this normal distribution will be our noise parameter, and of course we also need 500 points. And then we have the number that we multiply with x. Now of course we need to again add another random number to it, this would be this b, and also here we choose a random number from a normal distribution, but this time it is centered around b. And in this sense, we generate each value of y by multiplying the corresponding value in x with a random number that deviates slightly from 1, and we add to it another random number which deviates slightly from 4. And thus, this gives us two datasets that are linearly correlated with each other. So let's go back to the slides and remember what we actually have in real-life scenarios. In real-life scenarios, we don't have A or B available to us. The only thing that we have is this scatter plot, or just the data of x and the data of y. And now the challenge of linear regression is to just start from this data, these x and y points, and try to abstract the best A and B that link x and y. And that is what we will do next. And also, just not to lose track what we're doing here, once we have abstracted this a and b, we can use these numbers to make this formula connecting x and y, and thus this allows us to predict new values of y when we are given new values of x. So that is why we need to abstract the information of this a and b from our dataset. And to do this, we will actually learn from our underlying datasets by using an algorithm that tries to abstract a and b by just looking at our dataset. And the simplest algorithm is called linear regression. And in Python, this is just one line of code. But again, the hard part is not getting these numbers or implementing it in Python. No, the hard part is understanding what is going on under the hood. However, explaining the algorithm of linear regression, I will leave for the dedicated course on machine learning. So what does this Python function that implements linear regression on our datasets x and y, what does it actually return? Well, it returns a couple of things. First of all, the slope, which will be the value of our number a that we were looking for. Secondly, the intercept, which will be the value b that we were looking for. But also a p-value, which corresponds to the null hypothesis that a is equal to 0. So just to recap, this is the probability of finding this particular slope, or a more extreme value, under the null hypothesis that a is actually equal to 0. So the lower this p-value, the more confident you can be about this slope a. So for our example, meaning the data sets that we just generated in our Jupyter notebook, we get the following results. We get a slope or a value for A 1.04, and we get an intercept, or the value for B, of roughly 4. Now this means that we have a predicting linear curve of y is equal to this number A times x plus this number B. And the p-value is 0, so we can be very confident in both of these numbers. Now what is incredibly interesting here is that we indeed managed to find values for A and B that are incredibly close to the values that we started with. Remember, in our code, we set these values equal to A as 1 and B as 4. But in our actual data set, we smeared out this information by actually making random numbers from these values. The number that we multiplied x with was a number that was slightly different than A. And then we added a number that was slightly different than B. So we actually removed some information of these exact A and B from our data set. But the linear regression algorithm managed to look at only these two datasets with lacking information about A and B, and nonetheless managed to retrieve these values A and B again. For A we got very close to 1, and for B we got even closer to 4. And thus, whereas in reality we don't have access to these A and B, just the underlying datasets, linear regression nonetheless allows us to abstract an A and B that are very close to the real A and B of our underlying datasets. Now that we are given this formula that connects X and Y, we can use it to actually make new predictions. Now this means if we are given a new value of X, which wasn't present in our original dataset, for instance here we don't see any point at, let's say, minus 1.4, we can nonetheless predict a new value for Y, which means a value of Y that we expect to correspond to such a value of X. We just multiply this value of X with this new A that we found, and we add this B. And in fact, this formula can be represented visually by this straight line. And on this graph, this straight line represents the linear curve corresponding to the values of A and B that are obtained from this scatter plot, this dataset X and Y. And thus finding new values for Y corresponding to new values of X can be done visually as well. If we take a new value for X, which wasn't present in our original dataset, let's say minus 0.4 around here, we trace upwards towards this line, and then we trace to our Y value, then we get the corresponding Y value for this new X value, and thus a new prediction. But of course, this also goes the other way around, because remember, correlation does not mean causation. This can be very easily reversed. Let's say that we take a new value for Y, for instance, between 3 and 2.5, so 2.75, then we can predict a new X value that would correspond to this Y value. For instance, then we trace all the way here to the line, and then we trace down, and then we get roughly minus 1.2. Now let's map this on a concrete example, for instance, predicting house price from house size. Let's say that you have a data set with a lot of house sizes and a lot of corresponding house prices. Now from this data set, we can use linear regression to abstract an A and B that gives us a formula for connecting these two variables. Then if we're given a new house size, which wasn't present in our original data set, we can nonetheless predict a selling price for this house. But of course also vice versa. If we are given a new house price, then we can predict what the size of this house would have been, all thanks to linear regression. Now we need to talk about the errors of our prediction. And this can be done visually in the following way. Each green dot on this graph represents a real observation or a data point in our original data set. Each green dot has an X value, tracing vertically, and a Y value, tracing horizontally. However, if we for instance take this point right here, then we see that the predicted Y value for the X value corresponding to this point is much lower than the Y value of the actual point. So the Y value of this point is between 4 and 4.5. However, the predicted Y value for this X value, which can be found by tracing down along the vertical line until we cross our prediction curve and then tracing horizontally, is between 3.5 and 4. And thus we see that there is a large gap or an error in our prediction for points in our training data set. Now, this is of course not surprising, and due to the fact that our points here, our data sets, do not lie on an exact straight line. There is some noise in the system. You can imagine that if these points all lie on exactly a straight line, then our linear regression model will also predict an A and B that result in a red line that also lies on the exact same straight line as our data, and then there will be no difference between the predicted y values for our data points and the actual y values of our data points. And thus we conclude that for each x in our original data set, there are two values. We have the predicted y value, which we get by filling in this formula or tracing along this red line, and we have the real y value, which is the actual y value that we generated or that we observed in real-life scenarios. Now this allows us to define a residue, which is the difference between these two different y values. And doing this, we can actually visualize the errors of our prediction in the following way. As I said, the residue is the predicted y value, predicted by this formula right here that we found, and the real y value, which is just the y value of the underlying data. Now, if we make a scatter plot with on the x-axis our x values, our observations, and on the y-axis this residue, or this difference between these two y values, then we see the following scatter plot. Again, if our prediction is correct for each individual x value, then all of these residue values will lie on an exact line at 0. Now we can also see if we project all of these points onto the y-axis, so all the way to the right, then we get the histogram of our residue values. And by now you wouldn't be surprised that indeed these errors of our linear regression model are indeed normally distributed. So to end off, let's briefly go back to the code and see how we can actually implement this linear regression. And as said before, this is done with just one line of code, namely this one. What we do here is we define a lot of variables, the slope, which will be our value for A, the intercept, which will be the value for B, the R value, which I'm not going to talk about, and the P value, which is the p value corresponding to the null hypothesis that a, or this slope, is actually 0. And then we just call the function stats.linregress, which stands for linear regression, and we give it our two datasets, x and y. And then we run this cell and everything is done automatically. You will be given your a, your b, and your p value. Then you can use fprint statements to print these results. And then you can also define a y prediction. So for each x value in your x dataset, you can now make a prediction. You simply multiply it with the obtained slope from the linear regression, and you add to this the intercept, or this b value. Now, of course, this will give you a y prediction for which you can define the residuals, just your real y, so the observed y, minus the predicted y. And this gives you an idea of the error of your linear regression model. Now, of course, if you want to predict new y values for new x values, you just simply do the same. You multiply your slope, but now with new x values, whatever value that you can think of, or whatever value that you observe, and you add the same intercept. And in this way, you will get a y prediction, but now for new x values. And the rest of this code cell is basically plotting. So if we run this cell, then we see the following. We see indeed that again, this A is retrieved, which is roughly 1, B is also retrieved, and our linear curve will thus be the following. And just to show that it works without A and B being 1 and 4, we can change these. Let's say A is 1.9 and B is, let's say, 2. So if we run this again, then we will see the same thing. So we find for the slope 1.9, again really approximating our original A very well, and the intercept is also roughly 2. Now, of course, as is with any concept that we looked at thus far, if you want these retrieved values to be more accurate and more in line with the values that you set, you can of course always increase the number of data that you collect, which is again the same strategy as before. Just collect more data. And this is everything that we will discuss about linear regression in this bonus chapter. We will go into much more detail and, as I said, looking at what happens under the hood, how the algorithm works, in the dedicated course on machine learning. Now, in the next lesson, we will turn our attention to categorical values, and thereby we will introduce the first machine learning pipeline, which is needed to implement logistic regression. So I will see you there.